Okay, guys, so in this last remaining part of the design of LQR controllers, I want to talk about how to choose the Q and R matrices. Okay, so Q and R matrices are the design parameters of the LQR method. Okay, of the LQR controller. Okay, our question is how do we choose Q and R? Okay, often Q and R matrices are chosen as diagonal matrices. Diagonal matrices. The reason for that is that the function of Q and R is in the cost function to weight either the state or the input as an element of the cost function. So for example, if the Q matrix, which is the coefficient of the state, is large, and while R is small, an increase in the input would not have any drastic impact on the cost. Therefore, the algorithm will tend to make U larger. Therefore, it will have a more aggressive control input in order to reduce X much faster. But if on the other hand you have R being increased in comparison with Q, in that case, what you are telling the optimization is that you don't want to increase the input too much. Therefore, the algorithm is going to be much softer on trying to make X go to 0, but will not try to increase U that much. Okay. If we select Q and R as diagonal matrices, okay, we can still have an idea about which one of the inputs or which one of the states we do care more than the other ones. Okay, for example, here having for example Q2 too large means that you want the second state actually to go to 0 much faster than the other states. Okay, so the diagonal term indicates which component of the state will have a bigger influence in the cost function. So the algorithm, the optimization will be much more aggressive on that component of the state vector and pushes that one much faster to 0 so that the cost function does not increase that much. Okay, for the diagonal case, we have the cost function j of u of t will be our integral, the usual integral. But in this case, we will have, instead of the matrix multiplication, we will just have the summation of all the corresponding terms, qii, times xi square of t. So each entry of the state vector will be weighted by the corresponding term in that diagonal matrix. Okay. Similarly, with the inputs, where you have m inputs, 1 to m, you will have rjj uj square, and we will finish the integral. Okay. So that is one guideline. One of the guideline is that we select Q and R matrices as diagonal matrices. Another guideline, this one is known as the Bryson's rule, a general guideline on the magnitude of these QIIs and RJJs. This one is known as the Bryson's rule. Bryson's rule is that we can select QII as the inverse of the maximum acceptable value of xi square. Remember that it is an inverse relationship simply because of the fact that if we want to suppress xi, we want for it to have a larger contribution into the cost, so that the optimization actually suppresses that more. So if, for example, you have the maximum acceptable value of xi a larger value, that means you can allow xi to be larger. That means you assign a smaller value for qii, and that makes the contribution of the state in the cost function smaller. Okay. Similarly for rjj, basically we have the value of rjj set as the maximum acceptable value of uj square. So these are meant to be some initial selections, on Q and R. Let me give you an example, not a very complex example, just to give you how we translate these into some numbers. Okay. So let's say that we are given that a state is allowed to be within -7 and 5. So we are given some limits on what the state can be. So if we want to have the optimization kind of suppress xi to within those limits, we would set qii to be simply 1 over the square of -7, which is 49. Another example is, suppose we do not care about a value of a certain state, care about the value of xi. So we can represent that similarly with the representation that xi is within minus infinity and infinity, and that means qii is equal to 0. So if you set the corresponding value in the cost function, the value corresponding to a state, to 0, that means we don't care about what this particular value does in the cost function. As a final note, let me also Note that these selections are essentially some initial guesses, but they will not guarantee anything. Okay, these selections will not guarantee that the states or the inputs will remain within the given bounds. But they will certainly suppress those components to be most likely within the given bounds. Okay. If the bounds are not satisfied, in that case, meaning bounds are violated, you may need to increase corresponding QII and or RJJ by trial and error. Okay. So as a next, I will try to switch to my computer. Example on how we can design an LQR controller in MATLAB. Okay, so that's going to be my next discussion, and I want to do it not on my tablet but on my computer and try to record that example and how we can play around with some of the facilities in MATLAB.